So I need a tool that can help me basically work local opportunities and compare them to potential lithium ion battery solutions, right? It's hard to compare apples to apples, but I'm hoping that with your tool, we'll be able to show them potential degradation rates compared to a lithium ion application, depending on what's being used for. So that's where I am right now. So hopefully this tool will be able to bring in a lot of the sort of workload on my side, and the rest of it.
Got it. Got it. Okay. Well, I appreciate that overview, and that helps me a lot. Actually, our tool has been used to do exactly that, only instead of comparing lithium to an ultra capacitor, it's been used to compare lithium to another new technology that's called nickel hydrogen. The company that makes these batteries is called Enervenue. So similar to, as you mentioned, kind of there's superior battery life or cycle life for that technology, but less round trip efficiency, less or more self discharge. So kind of folks were, or our clients were looking for a tool to kind of compare apples to apples, performance of both technologies to each other. So I can actually share one of the reports here. Here, I'll just share my screen here real quick. So basically, this white paper, the our tool Storlytics was used to develop the results that are listed in this white paper. So you should be able to kind of do the same thing and come up with the same comparison between lithium and, but only here instead of Enervenue, just it would be your ultra cap, and it would be use case specific. So what you're trying to do with a battery makes a big difference in these technical scores. So that's obviously taken into account in our tool through kind of the time series dispatch profile here. We're calling it the POI profile. So that takes into account like the type of cycles you're doing, how often, and kind of gives you the analytics we'll go over today.
Right.
Right. So, and I can also share this white paper with you after our call if you want to dig into it more.
Thank you.
All right. So our tool is kind of, it has two modules in it. This is what the interface looks like. The first module is called the battery profile creator. The second is called the battery system modeler. The battery profile creator, its primary purpose is to support users in creating a PY profile, which is basically how the batteries are going to be utilized. So it's dependent on your exact use case, what you're trying to do with this battery system. Are you trying to, charge a battery from solar and discharge it later in the day, or are you participating in a market service, or are you PV smoothing? Just depending on what you're trying to do, this module helps you stack different applications on top of each other. So here, I'll just start us off with an example real quick. So this one is based on clipped energy storage. So here, we're assuming that, we're charging a battery from a renewable facility, in this case, solar. So we input the PV profile, and if there's a multiplier, we want to scale it by some factor, we can do that. But the logic of operation here is that when solar goes beyond a certain threshold that we specify here, called the charge threshold, you're charging from solar. And when it goes below a certain threshold, you start discharging. And you can turn one or both on at the same time. So in this case, we set it at 15 megawatts with a charge power ratio of 100%, which means if you have 16 megawatts, it'll be charging at 1 megawatt. Any questions about this clipped energy storage use case? What's like the logic of operation?
Yeah, I haven't actually heard flipped energy storage applications before. Is it sort of like peak demand, or well, I mean, so on solar, so it'd be like just your charge threshold. What would be a load profile or load maximum load of the load?
So the input profile would be either it's a generation profile, so that could be a PV profile, so kind of like your PV sys output, for example, or if you have a wind facility, just the time series of power production of that wind facility. Just as long as it's in CSV format and it just has the same format we're using, you can input it. So it's not a load, it's kind of a generation profile. We do have
Okay.
another use case here called peak load shaving. And in here, you kind of input a load profile. And basically, you set up the system so that you're discharging your battery when perhaps when load goes beyond a certain threshold and allowing it to charge when load is lower and then a certain threshold. So this could be used for applications like you mentioned, like demand charge management, demand response use cases, things like that.
So you can overlap the two of them, the generation and the load profile, and then come up with some type of
Yep. You can put all three of them together and you can either run them in priority mode, which means if any of them are occurring at the same time, it would prioritize based on this priority list here, right? Or you
okay.
can have it in stack mode where just all of them would be executed at the same time. So it just depends on what you're trying to do. So here, so in this application, what we're doing is, right now we set it up so that we're charging from solar when solar production goes beyond 15 megawatts. And here, what we're trying to do is, all right, now take that energy that we charge from solar and discharge it later in the day from 7 p.m. to 11 p.m. Right? So
Mhm.
let's just give that a run and we can go over the results.
Is there any way to sort of say if there's surplus power from the generation of PV, for example, as compared to the load, then they start say storing the energy?
Yes. So that's exactly what it would be doing. So here you're assuming that surplus power would be kind of you're saying anything beyond 15 megawatts in this case, but you can change this to whatever level you're targeting.
Right. So that 15 meg, you'd have to put that in as the threshold to say this is the peak load demand, basically across that load profile. That then you'd start storing the energy, not necessarily when there is a surplus. Like
Exactly.
let
Mhm.
okay.
And you can in the input. This is getting a little bit into the weeds, but in the input here, if you wanted to do that, you can basically have the PV profile minus load. So you can do that in Excel. And then that helps you kind
Right.
of, you know, really find out when excess solar production is happening and charge from it. In that case, you'd probably set the charge threshold here to 0. So that way you're planning to charge anything, any power from solar that is excess of load, because you would have
Right.
already taken out load from this profile.
Right. Right. And how many days? You've got 7 days in this file, but it could go for a month, whatever.
Yes, you can go really to 365 days. You can
Right.
go and you can be as granular as you want, down to 15 seconds, all the way up to 1 hour. So really, there's this countless number of use cases out there, a lot of things you can do with energy storage. So we built the
Mm,
software so that it's flexible and accommodates the wide variety of use cases out there.
okay.
Right. So right now I just hit generate report, and then that'll basically generate the results from this simulation. This is what the results look like. It starts off with just our inputs. So I won't go over that since we discussed it, but then it lays out kind of the analytics for each use case. So starting out with, in this case, PV clipped energy storage app shows us really when we're charging from solar. So remember, we had 7 days of solar production, each one with different, one was clear, the others had cloudy days, and these two apparently were overcast or something. But it gives you kind of the maximum charge, power and energy, and maximum discharge. So we had set discharge here to off, so that's why it's showing zeros. But
Sorry,
then
what did you have at off?
here, the discharge. So we weren't
Mhm.
using this discharge threshold. Instead, we
Right.
used basically this equalize daily discharge and charge energy, which is basically on a daily basis, taking the energy that was charged and discharging it later in the day between 7
Right.
and 11. So that's the next application here, right? Daily energy charge discharge. And it shows you that, all right, between 7 p.m. and 11 p.m., we discharged whatever energy we were collecting during those days, or on each
Mm,
day, rather.
right.
So then things are kind of put together in the full profile analytics section. It shows you, all right, when you were charging over a 24-hour period, when you were discharging, right? And of course, here, these analytics are really helpful in just telling you, what was the maximum energy you needed to charge, maximum energy you needed to discharge, and same for power. So this helps you kind of size your system. Now, if you wanted to size your system based on the maximums, you would use this, but here we have cumulative distribution functions that show you, all right, how often did you get points that were at 9 megawatts, right? So that helps you kind of avoid, designing a very, very expensive system for just one day of operation. So it just tells you here how often different power points are occurring for both charge here in orange and discharge in blue. So for example, here, the power here is almost linearly increasing here. So, I mean, here it would make sense to charge it, to size the system based on uh, the maximums. But if you look at energy here, right? So here you can see that with 15 megawatt hours, you're capturing kind of 70% of the days. So the question becomes, all right, is doubling the energy capacity of the battery system really worth that additional 30% of the days? So that's kind of
Right.
an economic question. So that's basically the battery profile creator report. And then here you can just generate output CSVs. So kind of similar to PV system, will give you all the details in a CSV format. So I'll just go over that here real quick.
You can play with the data, present it as you want.
Exactly. If you wanted to do any post processing, you can obviously do that. But here it kind of gives you all those details here for the simulation.
Mhm.
All right, now moving to the battery system modeler. Now, this is where really the detailed analytics take place. Now, everything we did was, to, of course, produce those analytics, but additionally create this POI profile, which I already have loaded here.
Yeah.
And then from there, I can input a TMY3 file that takes into account the temperature of the region, like the climate of the region in which I'm installing this battery system. And this is because it really makes a difference in any technology. So for lithium, if you're installing a battery in the Mojave Desert, it's going to require much more ox load than if you were installing it in North Carolina or somewhere else. So
Sure.
you really need to take into account the TMY3 profile of the area of the region you're installing. And then next step is to specify the equipment models. Now here, this is where, for your case, if you're, since you're trying to simulate ultra caps, you can create a .btt file for your ultra cap technology. So here we mentioned the Enervenue example here. So we created a model for them here, which supported basically the simulations that helped us deduce the results here to estimate the cost of the project. We're using the two different technologies and overall, not just capital cost, but overall cost of ownership, because we're able to estimate, energy losses throughout project life for both.
Nice.
Right.
Does
So
this allow for like augmentation of the batteries to hit certain renewable energy mix requirements or things like that?
yeah, exactly. So once you run a simulation, you can deduce the degradation profile
Mm.
of the technology you're using. And from there, if you're targeting an augmentation strategy, you can design it accordingly based on how much degradation you're getting.
Okay.
So here, for your case, since you're trying to simulate ultra cap performance, you can vary the parameters in the .btt file here based on your ultra cap technology. And with the license, you will get a battery model construction guide that helps you fill out these parameters for your technology.
Cool.
Right. So here we were simulating a generic lithium iron phosphate. And then here you basically specify the sizing of your system. So while you're doing that, you're comparing the values here under user design, both system power and energy, to what was needed within the POI profile that you inputted. So here, maximum discharge and charge was 8 megawatts and 9.6 megawatts. And
Mhm.
maximum discharge energy and charge energy was 32 megawatt hours and 37.5 megawatt hours, respectively. So, as you can see here, our sizing here is adequate. We're at 44, almost 45 megawatt hours and 11 megawatts, which covers the capacities we have here. And then here we can set the operational limits. So maximum state of charge that we're planning to run our system at, minimum state of charge, and of course, the initial state of charge for the simulation. And final thing to set here is the state of health or the degradation parameters. So here we're starting with a state of health of 1 and assuming a year life of 20 years so that we can get the degradation profile of over 20 years implementing the use case that we have here.
Nice.
So
And the
there,
initial state of health, is that sort of like the initial usable capacity as opposed to nominal capacity or?
exactly. It could be used as what you just described is basically depth of discharge, but it could be used or it is intended for the basically how much your batteries have degraded. So if you're doing an augmentation project, you may want to start your simulation at a slightly degraded level. So you're assuming that, for example, your cells have reached a 90% state of health, which is basically the maximum energy capacity cells can take compared to what they could take when they were new, right?
Okay. So
So
you sort of with the augmentation, you'd have to do sort of a series of these models to, and then sort of get the CSV file and cut and paste almost like.
correct, correct. So depending on really what your exact augmentation strategy, because there's a number of them out there. You can do AC augmentation, which is basically adding inverters as the project kind of life extends. Or there's also DC augmentation, where you're adding battery racks, to already existing inverters. And then there's also DC augmentation with using DC-DC converters, where you're adding the new racks behind new DC-DC converters. So really, it depends on which strategy you have, and based on that, you kind of structure the simulation. But yes, for each phase, you would need to run a separate simulation.
Right.
So I just ran this and generated the report here. Right. So it starts off with basically all your inputs, the POI profile, the battery model details, the inverter model details, and loss assumptions, operational constraints, and our degradation assumptions. So the actual analytical section starts off with the power dispatch adequacy. And here it just tells you, all right, out of your profile, how adequate was this battery system in meeting required power at different points on the project, right? So at the POI for charging, were your inverters large enough to be able to charge what seems to be here 9.6 megawatts? So as you can see here, yep, we adequately size our battery system from a power standpoint, because all the the power set points in our POI profile were met. Now here we do the same thing for energy, right? So at the POI here, for example, our POI profile had 104.5 megawatt hours of throughput that needed to be charged. So out of that, we were able to charge 103.2 megawatt hours, right? So it tells you really how closely you were able to follow the signal in the POI profile. Now you may be asking, all right,
Mhm.
why didn't I meet 100% of this, right? Here my battery was 44.7 megawatt hours, and maximum energy charged in the day was 37.5 megawatt hours. So what you will find here when you get kind of deeper into the report was that on the fourth day here, you charged to the maximum state of charge, which is 95% in this case, because we set it that way here. So when the next day started and you wanted to charge, you were already here, right? So you couldn't charge anymore. So
Right.
that's
You
what
didn't use that whole. You didn't use the stored energy on that night or time shift.
exactly. So here you didn't you the so let's look at it a little bit closer. So here you started off and you charge energy and discharge it. That's kind of what the use case is, right? And we started from 40% state of charge, right? So we started here, right? So each day we're charging and discharging, charging and discharging. But each day, since there are losses, kind of you're going down a bit. And also, you have to remember when we created this POI profile, we were assuming a round trip efficiency of 85%, right? So with time, you're actually losing energy because, batteries aren't ideal, right? There's some
Mhm.
losses in there. Now, when you
And
came
if it's coupled with a solar PV system, I mean, it's only as good as how much sunlight is available on any given day to
exactly,
charge surplusage storage, right? Or surplusage load. So,
exactly. So here on a couple of days, you may remember on days one, I think two, it was overcast, right? So here,
mhm,
yeah, there was hardly any energy because we set the charge threshold at 15 megawatt hours,
yeah,
and here it barely
megawatts,
passed that. Yeah. So, you're just losing energy those 2 days that nothing came from solar.
right?
But then when you came here this day where it was a lot of sunlight, you were already at, I think, 30% state of charge or so. Right. So you kind of charged till you reached the maximum capacity because you started at 30% already. So that's what
Mhm.
created this delta here, right? You only achieved 98.8% of the POI. So this kind of, so we went through the energy chart. This next one here is basically summarizes both power adequacy and the energy adequacy of this battery system. So the orange here is energy and the blue is power. So you can see the blue is 100% all around. And just briefly, so here, these different axes are, POI, inverter, battery, internal to the battery. This is all charging. And then from here, it's discharging. So internal to the battery, inverter, and then POI, all discharging. So it kind of tells you, right, charging to discharging, how did you do at different points?
Okay.
Then you kind of get into system efficiency analytics. So overall, what was your round trip efficiency for this system? So here you're at 77.8% round trip efficiency, which, you know, may strike some people as, wow, that's really low for lithium, right? But really, when you think about it, a battery system that is not dispatching is a load. So remember, we had 2 days that we really weren't doing anything, right?
Mhm.
There was no energy to charge, and accordingly, there was no energy to discharge. So the battery system is just going to be sitting there cooling the cells, right? Now, if you're in a very
Right.
hot region, that cooling is going to be a lot. If you're in a mildly tempered region, that's it's going to be less. But there will be energy losses that are pulled by the HVAC or the auxiliary load. So that shows kind of here, right? Aux energy fed here during charging and aux energy fed during discharging. Here we have 14.7%. So that's what basically caused, where do we go here? Yeah, the kind of lower than usual round trip efficiency.
Mm, right. Right. Because of the 2 days of power consumption of the storage system as opposed to being able to increase the storage and surplus and then use it later on in that day just didn't happen. So, okay.
Exactly, exactly. Right. So then it gives you analytics on the throughput at different points in the project. So this is
Mhm.
important for kind of performance guarantees, right? So how many cycles you exerted each day in cycles and in discharge throughput. So as you can see here, days 1 and 2, there was basically zero. We didn't have the battery really didn't do anything because it was overcast.
Right.
Then we went through this one, the state of charge. So I'll just clarify the blue bar here just shows the minimum and maximum. And the red dots is the average
Which
during that day.
so because there's only one charge cycle per day, it was sort of the maximum was where it started, and the minimum was where it ended up, basically.
Yeah, yeah. So
Wasn't really.
not necessarily. Yeah, exactly. So here, it just shows the minimum and the maximum. It doesn't show really where you started and ended. So we know for a fact here that on the first day we started at where was it? Yeah, 40%. So here, like it just went slightly below that 40% here, but we
Mhm.
started exactly at 40% here.
So it was mostly charging to that day, then.
Exactly. Exactly. So it charged. So for this day, it charged and discharged 85% of what it charged.
Okay.
So we can say it kind of ended probably around here because the next day,
Or 85% of what it charged, or 85% of the entire battery. Like,
85% of what it charged. Because here in the battery profile creator, we set it up so that the POI profile would discharge 85% of what it charges.
okay. So not necessarily 85% of 100% of battery potential.
Exactly. Exactly.
Okay.
Right. Now, here, this talks about C rate, which is kind of needed for a lot of things.
All right. So that was the round trip efficiency, not the state of charge then. Because the round trip efficiency would be you can only discharge certain percentage of the entire battery, right?
So, round trip efficiency, the, 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 the meaning of round trip efficiency, it refers to kind of the efficiency from a round trip. So, if you charged basically 100 and you received or able to get out 75, then 75 divided 100, that's 75%, for example.
Hmm.
But if you do that same thing and you're using, let's just say, a 200 megawatt hour battery, right? It really doesn't have an effect on the round trip efficiency value itself. So the metric is really, of course, the technology has an effect on what the metric ends up being. But in this case, we specified this round trip efficiency even before we kind of selected even a technology here. So we're just, set it up so that we're discharging the POI profile that we create is discharging 75 or 85% of what it charges. So that way,
Right.
when we feed it here, because we know we're going to have losses in the medium voltage transformer, in the
Yep.
inverter, in the battery. So
Right.
that way, when these losses happen, right, they're already, in the sense, accounted for. Of course, it's not, when we're creating the profile, it's not going to be 100% accurate, right? That's why, it's kind of like a chicken and egg situation, right? You're creating the profile, assuming a certain technology. You know that that technology on average is 85% round trip efficient. But when you actually run the simulation, you get the exact round trip efficiency and it changes every day, right? So, like we've seen here, the overall round trip efficiency for the 7 days we simulated ended up being 77.8%. So it's kind
Hmm.
of, this original this 85% round trip efficiency, this is just an estimation so that we're realistic about what to expect at the POI profile, since this is where
Okay.
we're putting the signal.
Reusable storage available.
Exactly. You got it. Right. So then here, C rate here, it refers to kind of now at the battery terminals, what percentage of the rated energy was kind of requested. So here got 0.21 and here 0.19. That was the maximum. And average was very, very low because we were dispatching the system very often. And then
Right.
same thing here, it kind of for C rate, it tells you, all right, what was the maximum charge C rate, maximum discharge C rate, and the average of charging here in red, and the average of discharging here as a green dot. Now, most importantly here, the degradation. This is kind of what most financial folks are interested in, how the battery degraded over time,
Yeah.
because that specifies, all right, how much battery capacity am I going to purchase at year zero? How much do I need to oversize the system? Right. So in
Right.
this
Right.
case, we're degrading down to 35 megawatt hours. If I wanted to keep the system at 40 megawatt hours throughout its life, I would need to oversize it quite a bit to make sure that by year 20, if I'm targeting a 20-year life, I would end up here with 40, excuse me, 40 megawatt hours.
Right. Right. Yeah, that's pretty helpful for us. Interesting.
All right. So any questions about degradation?
No, no, I mean that's fairly clear. I mean, would we have we would have guidance on setting up that battery profile file, right? I think the battery manufacturer needs to provide all those inputs.
Oh, the BTT file here?
Yeah.
Yes. So we will provide with your license a guide on how to fill out these different parameters for your battery technology, and we'll even
Mhm.
support you with it. So here, these are our tiers here. So the one I wanted I want to bring your attention to is Advantage and Premier. Those come with energy storage services. So Advantage, I don't know why my cursor isn't showing here, but
I see
anyway,
it.
all right.
Mhm.
Yep, it's here. It's tiny. All right. Advantage comes in with 30 hours of energy source services support, and Premier comes with 60 hours. So what that basically is, I mean, you're running Storlytics, you're trying to do something with it, and you either want help optimizing a project or building a new battery file. We basically support you and help you out up to kind of the hours here per year. So I think this would be kind of helpful to you. So this is different. Some people kind of confuse this with software support. All of our tiers have software support. So if you have any issues, you're trying to do something with Storlytics, you have questions, yeah, we'll definitely support you there with Storlytics Base and Plus. But Advantage and Premier, this is kind of the next level where you're getting actual subject matter expert engineers supporting you with exactly what you're trying to do and running simulations for you if need be.
Great.
All
That'd be
right,
very helpful.
great. So with that, I think, do you have any questions about the software or in general?
Do you guys have like ancillary services modeling?
So do you mean following a signal from like
Agreed.
an
Yeah.
ISO or, yep. So basically, in storage services, we actually have an example here for a PJM signal. So here, this is a PJM frequency rank D signal, right? So you can either select that, or if you're in any another market, you can get the signal from it. All you need to do is just input it here and just set the same parameters we did and simulate that.
Okay.